Now we are seeing about the mathematical forms here, means the convex lens formulas. Lens formula we are seeing. Okay, just like the mirror formula, మనం ఇప్పుడు lens formula చూస్తున్నాం. 1/f is equal to 1/v plus 1/u. ఇది మనం మిర్రర్ ఫార్ములాలో చూసాం. 1/f is equal to 1/v plus 1/u, that is. f అంటే ఇక్కడ ఫోకల్ లెంగ్త్, u అంటే ఆబ్జెక్ట్ డిస్టెన్స్, v అంటే ఇమేజ్ డిస్టెన్స్. అయితే ఫోకల్ లెంగ్త్ అంటే అది మనకి ఆప్టిక్ సెంటర్ నుంచి ప్రిన్సిపల్ ఫోకస్ వరకు ఉండే డిస్టెన్స్ని మనం ఫోకల్ లెంగ్త్ అంటాము. అలాగే ఆబ్జెక్ట్ డిస్టెన్స్ అంటే ఆప్టిక్ సెంటర్ నుంచి ఆబ్జెక్ట్కి ఉండే డిస్టెన్స్ని ఆబ్జెక్ట్ డిస్టెన్స్. అలాగే ఇమేజ్ డిస్టెన్స్ అంటే ఇమేజ్ పొజిషన్ నుంచి ఆప్టిక్ సెంటర్ ఉండే డిస్టెన్స్ని ఇమేజ్ డిస్టెన్స్ అంటాం. ఓకే, బట్ ఇదేంటంటే స్పెరికల్ మిర్రర్స్కి మనం యూజ్ చేసిన ఫార్ములా. అలాగే మనకి ఇప్పుడు స్పెరికల్ లెన్స్లో రిఫ్రాక్షన్ జరుగుతుంది కాబట్టి హియర్ మనకి 1/f is equal to 1/v minus 1/u అవుతుంది. ఎందుకంటే ఇక్కడ ఆబ్జెక్ట్ డిస్టెన్స్, ఇమేజ్ డిస్టెన్స్ మనకి రిఫ్లెక్షన్లో ఏమవుతుందంటే ఆఫ్టర్ రిఫ్లెక్షన్ లైట్ రేస్ ఆర్ కమింగ్ బ్యాక్ టు ద సేమ్ మీడియం. అందుకే యూకి ఏదైతే కన్వెన్షన్ ఉంటుందో వీకి కూడా అదే కన్వెన్షన్ వస్తుంది. అందుకే 1/f equal to 1/v plus 1/u రాస్తాం. బట్ కానీ ఇక్కడ రిఫ్రాక్షన్లో లైట్ రేస్ ఒక మీడియం నుంచి ఇంకొక మీడియంలోకి వెళ్తాయి. అందుకనే 1/f is equal to 1/v minus 1/u మనం తీసుకుంటున్నాం. అలాగే f అంటే మళ్ళీ ఇక్కడ సేమ్ ఫోకల్ లెంగ్త్, u అంటే ఆబ్జెక్ట్ డిస్టెన్స్, v అంటే ఇమేజ్ డిస్టెన్స్. ఓకే, సో ఇది మనకి లెన్స్ ఫార్ములా అవుతుంది. అయితే ఈ లెన్స్ ఫార్ములా యూజ్ చేయడానికి మనకు కొన్ని మళ్ళీ రూల్స్ ఉన్నాయి. ఓకే, బికాస్ ఎఫ్, యు అండ్ వి ఆల్ దీస్ ఆర్ డిస్టెన్సెస్. యాజ్ ఆల్ ఆర్ డిస్టెన్సెస్ కాబట్టి ఆల్ ద డిస్టెన్సెస్ వీ హ్యావ్ టు మెజర్ సమ్ పర్టికులర్ పాయింట్. దట్ పాయింట్ వీ కాల్ దట్ హియర్ యాజ్ ఆప్టిక్ సెంటర్. అదే మనకి యాక్చువల్గా ఆరిజిన్ లాగా యాక్ట్ చేస్తుంది ఇక్కడ. సో ఫర్ ఎగ్జాంపుల్ మనం ఒక కాన్వెక్స్ లెన్స్ కనుక తీసుకుంటే ఇది ఆప్టిక్ సెంటర్. హియర్ మనం ఆబ్జెక్ట్ ఈజ్ ఎట్ హియర్ అండ్ డ్యూ టు రిఫ్రాక్షన్ ద ఇమేజ్ ఇస్ ఫ్రమ్ అదర్ సైడ్. ఓకే, దెన్ హియర్ ఫోకస్ ఫర్ కాన్వెక్స్ లెన్స్ యాక్చువల్గా అది మనకి రియల్ ఫోకస్ ఉంటుంది. రియల్ ఫోకస్ అంటే దట్ ఫోకస్ ఇస్ ఫార్మ్డ్ ఆఫ్టర్ ద లెన్స్ అనమాట. ఓకే, నా ఇందులో ఫోకల్ లెంగ్త్ ఎఫ్ అంటే డిస్టెన్స్ ఫ్రమ్ ఆబ్జెక్ట్ టు ఫోకస్ అండ్ ఆబ్జెక్ట్ డిస్టెన్స్ అంటే ఆప్టిక్ సెంటర్ నుంచి ఆబ్జెక్ట్కి ఉండే డిస్టెన్స్. అలాగే ఇమేజ్ డిస్టెన్స్ అంటే ఇమేజ్ నుంచి ఆప్టిక్ సెంటర్కి ఉండే డిస్టెన్స్ అనమాట. అయితే ఇందులో మనం అకార్డింగ్ టు రూల్ 1 మనం రూల్ 1ని తీసుకుంటే in 1/f is equal to 1/v minus 1/u, then here f, v and u all three are distances there. So while measuring these distances we have to start from origin. We should have a starting point. That starting point is nothing but our optic center here. Okay, so that's why here while taking the focal length here first f, we have to take the distance starting from optic center and we have to take up to the focus. ఈ డిస్టెన్స్ని మనం ఫోకల్ లెంగ్త్ అంటాం. ఓకే, అదేవిధంగా ఇప్పుడు మనం ఆబ్జెక్ట్ డిస్టెన్స్ తీసుకుంటే ఆప్టిక్ సెంటర్ నుంచి ఆబ్జెక్ట్కి ఉండే డిస్టెన్స్ని ఆబ్జెక్ట్ డిస్టెన్స్ అంటాం. ఓకే, అలాగే ఆప్టిక్ సెంటర్ నుంచి ఇమేజ్కి వచ్చే డిస్టెన్స్ని ఇమేజ్ డిస్టెన్స్ అంటాం. ఇది ఎఫ్, యు అండ్ వి. This is our rule 1. So what is this rule 1? Any distance you measure, any distance should be measured starting from optic center. ఓకే, ఇది మనకి రూల్ 1. ఓకే, సీ దట్ ఎనీ డిస్టెన్స్ షుడ్ బి మెజర్డ్ స్టార్టింగ్ ఫ్రమ్ ది ఆప్టిక్ సెంటర్ ఓన్లీ. అందుకే ఇక్కడ మనకి ఆబ్జెక్ట్ డిస్టెన్స్ ఏమో ఇక్కడ ఉంది, ఆప్టిక్ సెంటర్ ఇక్కడ ఉంది. సో దట్స్ వై వీఆర్ టేకింగ్ స్టార్టింగ్ ఫ్రమ్ ది ఆప్టిక్ సెంటర్ అండ్ వీఆర్ గోయింగ్ టువర్డ్స్ ది ఆబ్జెక్ట్. అలాగే ఇమేజ్ డిస్టెన్స్కి స్టార్టింగ్ ఫ్రమ్ ది ఆప్టిక్ సెంటర్ మనం వీఆర్ ఫైండింగ్ ద ఇమేజ్ డిస్టెన్స్ లైక్ దిస్. అండ్ ఇన్ ద సేమ్ వే ఫర్ ఫోకస్ here we are taking the focal length starting from optic center going towards the focus అన్నమాట. తర్వాత రూల్ 2. యాక్చువల్గా మనకి రూల్ 2 ఇట్ డిసైడ్స్ ద సైన్ కన్వెన్షన్. ఏ సైన్ యూస్ చేయాలనేది డిసైడ్ చేసేది రూల్ 2. ఓకే, సో హౌ టు టేక్ దిస్ రూల్ 2 ఈజ్ whenever if you are measuring the distances, we already measured distances f, u and v starting from optic center. Now if you are taking these distances, ఏవైతే మనం డిస్టెన్స్ మెజర్ చేసామో ఆప్టిక్ సెంటర్ నుంచి ఆ డిస్టెన్సెస్ మెజర్ చేసిన డైరెక్షన్ కనుక ఇన్సిడెంట్ లైట్ రేకి, ఇది మనకి ఇన్సిడెంట్ లైట్ రే విచ్ ఫాల్స్ ఆన్ ది లెన్స్ అన్నమాట. ఓకే, ఏ డిస్టెన్స్ అయితే మెజర్ చేసిన డైరెక్షన్ ఆపోజిట్ టు ఇన్సిడెంట్ లైట్ రే ఉందో అది మైనస్ కింద తీసుకుంటాం. అలాగే ఇఫ్ ద ఇన్సిడెంట్ లైట్ రే డైరెక్షన్ మెజర్ చేసిన డిస్టెన్స్ డైరెక్షన్ రెండు ఒకటే డైరెక్షన్లో ఉంటే అదేమో పాజిటివ్ కింద తీసుకుంటాం అన్నమాట. అంటే డిస్టెన్స్ మెజర్డ్ ఇన్ ద డైరెక్షన్ ఆఫ్ ఇన్సిడెంట్ లైట్ రే ఈజ్ టేకెన్ యాజ్ పాజిటివ్, opposite to the incident ray is negative అన్నమాట. అలాగే ఎగ్జాంపుల్ ఇక్కడ మనకున్న కాన్వెక్స్ లెన్స్ కనుక తీసుకుంటే హియర్ ఇది ఇన్సిడెంట్ రే, ఇది ఫోకల్ లెంగ్త్. ఫోకల్ లెంగ్త్ డైరెక్షన్ మెజర్ చేసింది ఇన్సిడెంట్ లైట్ రే డైరెక్షన్, ఈ రెండు ఒకటే డైరెక్షన్లో ఉంటాయి. అందుకే ఎఫ్ ఈజ్ పాజిటివ్ హియర్ ఫర్ అవర్ కాన్వెక్స్ లెన్స్. ఓకే, అలాగే ఇప్పుడు ఆబ్జెక్ట్ డిస్టెన్స్ తీసుకుంటే ఆబ్జెక్ట్ డిస్టెన్స్ ఓ నుంచి ఆబ్జెక్ట్ సైడ్ వెళ్తున్నాం, ఈ డిస్టెన్స్ ఇన్సిడెంట్ రే డైరెక్షన్ ఓ నుంచి లెన్స్ వైపు వెళ్తుంది. అంటే బోత్ ఆర్ ఆపోజిట్ టు ఈచ్ అదర్ అనమాట. అందుకే యు ఈజ్ నెగిటివ్ అవుతుంది అకార్డింగ్ టు ద రూల్. అండ్ వెన్ కమ్ టు ఇమేజ్ డిస్టెన్స్ ఓ నుంచి ఐకి వెళ్తుంది, అలాగే ఇన్సిడెంట్ రే ఆల్సో గోయింగ్ టువర్డ్స్ ఇన్ ద సేమ్ డైరెక్షన్. అందుకే ఆ రెండు కూడా ఒకటే డైరెక్షన్లో ఉన్నాయి కాబట్టి v ఈజ్ టేకెన్ యాజ్ పాజిటివ్ హియర్ లైక్ దిస్. f ఈజ్ పాజిటివ్, u ఈజ్ నెగిటివ్ అండ్ v ఈజ్ పాజిటివ్ అగైన్. ఓకే, ఇది మనకి కాన్వెక్స్ లెన్స్లో వచ్చేది. అలాగే ఇంకొక ఇంపార్టెంట్ రూల్ 3 ఉంది మనకి. రూల్ 3 ఏంటంటే ఎనీ ఆఫ్ ద డిస్టెన్స్ వి మెజర్, ఏ డిస్టెన్స్ అయినా కానీ when you are measuring above the principal axis. Okay, so like here in case of object distance you see object here. So in case of object మనం ఆబ్జెక్ట్ని అబోవ్ ద ప్రిన్సిపల్ యాక్సిస్ తీసుకున్నాం. ఇలా అబోవ్ ద ప్రిన్సిపల్ యాక్సిస్ తీసుకున్నప్పుడు ఏ డిస్టెన్స్ అయినా కానీ పాజిటివ్గా తీసుకుంటాం. అలాగే ఎప్పుడైనా మనం ఇమేజ్ డిస్టెన్స్ని మెజర్ చేసేటప్పుడు లైక్ హియర్ ఇన్ దిస్ కేస్, ఓకే, ఎప్పుడైనా డిస్టెన్స్ మెజర్మెంట్ కనుక బిలో ద ప్రిన్సిపల్ యాక్సిస్ కనుక ఉంటే దాన్ని మనం నెగిటివ్ కింద తీసుకుంటాం. అంటే రూల్ 3 టెల్స్ దట్ డిస్టెన్స్ మెజర్డ్ above the principal axis is positive, and if you are taking below principal axis అది మనకి నెగిటివ్ అవుతుంది. ఓకే, డిస్టెన్స్ మెజర్డ్ అబోవ్ ద ప్రిన్సిపల్ యాక్సిస్ పాజిటివ్, బిలో ద ప్రిన్సిపల్ యాక్సిస్ నెగిటివ్ అవుతుంది అన్నమాట. ఓకే, సో ముఖ్యంగా మనం ఈ 3 రూల్స్ ఫాలో అవ్వాలి. ఓకే, సో ఫస్ట్ రూల్ ప్రకారం ఎనీ డిస్టెన్స్ వీఆర్ మెజరింగ్ వీ హ్యావ్ టు స్టార్ట్ ఫ్రమ్ అవర్ ఆరిజిన్ ఈజ్ నథింగ్ బట్ ద సెంటర్ ఆఫ్ ది లెన్స్. Okay, always we have to start the distance to measure only from the center of the lens here. అయితే సెకండ్ రూల్ ప్రకారం whatever the distance we are measuring, u కానీ f కానీ v కానీ any of the distance we measure here, if it is in the direction of incident light ray, అంటే మనకి లైట్ రే ఇన్సిడెంట్ అయ్యే డైరెక్షను మనం డిస్టెన్స్ మెజర్ చేసిన డైరెక్షను ఈ రెండు ఒకటే డైరెక్షన్లో కనుక ఉంటే దాన్ని పాజిటివ్ కింద తీసుకుంటాం, లేదా ఆపోజిట్గా ఉంటే కనుక నెగిటివ్ కింద తీసుకుంటాం. అలాగే రూల్ 3 అదేంటంటే ఇఫ్ ఆబ్జెక్ట్ డిస్టెన్స్ ఆర్ ఇమేజ్ డిస్టెన్స్ హియర్ వీఆర్ టేకింగ్ పాజిటివ్ నెగిటివ్, బట్ ఇన్ ద సేమ్ వే వీఆర్ హ్యావింగ్ వన్ మోర్ ఇస్ దేర్ దట్ ఈస్ అబౌట్ height of the object, height of the image. So if you are taking the height there above the principal axis, so if మనకు హైట్ని మనం above the principal axisతో మెజర్ చేస్తూ ఉంటే అదేమో పాజిటివ్ అవుతుంది, ఎప్పుడైతే హైట్ని మనం బిలో ద ప్రిన్సిపల్ యాక్సిస్ మెజర్ చేస్తుంటే అదేమో నెగిటివ్ అవుతుంది. ఓకే, సో డిస్టెన్స్ మెజర్డ్ అబోవ్ ప్రిన్సిపల్ యాక్సిస్ పాజిటివ్, డిస్టెన్స్ మెజర్డ్ బిలో ద ప్రిన్సిపల్ యాక్సిస్ ఇస్ టేకెన్ యాజ్ నెగిటివ్. అలా రూల్స్ మనం ఫాలో అయితే మనకి ఫోకల్ లెంగ్త్ పాజిటివ్, ఆబ్జెక్ట్ డిస్టెన్స్ నెగిటివ్ అండ్ ఇమేజ్ డిస్టెన్స్ ఆల్సో పాజిటివ్ ఫర్ కాన్వెక్స్. దిస్ ఇస్ ఫర్ కాన్వెక్స్ లెన్స్. ఓకే, ఇదే విధంగా మనం కాన్కేవ్ లెన్స్ కూడా ఇలాగే తీసుకుంటే ఫాలోయింగ్ ద సేమ్ రూల్స్. నౌ కాన్కేవ్ లెన్స్కి, బట్ కాన్కేవ్ లెన్స్ నేచర్ డైవర్జింగ్ నేచర్ వల్ల దాని ఫోకస్ ఏంటంటే మనకి సేమ్ సైడ్ వస్తుంది, బికాస్ దట్ ఈస్ హ్యావింగ్ వర్చువల్, దట్ ఈస్ ఇది ఆబ్జెక్ట్ ఆప్టిక్ సెంటర్ అండ్ ఫోకస్ మనకి సేమ్ సైడే ఉంటుంది బికాస్ ఆఫ్ డ్యూ టు వర్చువల్ నేచర్. ఓకే, అండ్ ఇఫ్ దిస్ ఈజ్ ది ఆబ్జెక్ట్, ఓకే, మనకి ఇమేజ్ కూడా కాన్కేవ్ లెన్స్లో మనం ఆల్రెడీ రే డయాగ్రామ్స్లో చూసాం, ఇమేజ్ ఈజ్ ఆల్సో ఫార్మింగ్ ఆన్ ది సేమ్ సైడ్ హియర్. ఓకే, ఇది ఆబ్జెక్ట్, ఇదేమో ఇమేజ్ అవుతుంది. ఓకే, నౌ ఇప్పుడు మనం రూల్ 1ని ఫాలో అయితే ఎనీ డిస్టెన్స్ షుడ్ బి మెజర్డ్, యూ షుడ్ స్టార్ట్ ఫ్రమ్ ఆప్టిక్ సెంటర్ విచ్ ఈజ్ అవర్ ఆరిజిన్ హియర్. So this is our optic center. Now I am measuring the distance f here, this distance. So I have to start from the O and we are taking up to the f there. దీన్ని మనం ఫోకల్ లెంగ్త్ అంటాం. ఓకే, నెక్స్ట్ వన్ మనం ఆబ్జెక్ట్ డిస్టెన్స్ తీసుకోవాలి ఆప్టిక్ సెంటర్ నుంచి ఆబ్జెక్ట్ వరకు. దిస్ ఈజ్ ద ఆబ్జెక్ట్ డిస్టెన్స్ దట్ ఈస్ విచ్ ఈజ్ u. అండ్ నెక్స్ట్ వన్ మనం ఫ్రమ్ ఆప్టిక్ సెంటర్ టు ఇమేజ్ తీసుకుంటున్నాం. దిస్ ఈజ్ కాల్డ్ ఇమేజ్ డిస్టెన్స్ v, that is. Now we got all the three distances there, f we got, v we got and u also we got. Now if you follow the rule 2, whatever the distance we are measuring in the direction of incident light ray, so incident light ray మనకి ఎప్పుడు కూడా ఆబ్జెక్ట్ నుంచి స్టార్ట్ అయ్యి లెన్స్ వైపు వెళ్తూ ఉంటుంది ఇలాగా. దిస్ ఈజ్ అవర్ ఇన్సిడెంట్ రే. ఓకే, సో అయితే ఇక్కడ ఆబ్జెక్ట్ నుంచి ఇన్సిడెంట్ లైట్ రే స్టార్ట్ అయినప్పుడు హియర్ ఫోకల్ లెంగ్త్, ఇన్సిడెంట్ రే రెండు కూడా ఆపోజిట్ డైరెక్షన్లో ఉన్నాయి ఇక్కడ. బికాస్ మనం ఫోకల్ లెంగ్త్ని మెజర్ చేసేటప్పుడు ఆప్టిక్ సెంటర్ నుంచి స్టార్ట్ అయ్యి ఫోకస్ సైడ్ వెళ్తూ ఉంటాం, ఇక్కడేమో ఆబ్జెక్ట్ నుంచి స్టార్ట్ అయ్యి టువర్డ్స్ ద లెన్స్ ఏమో ఆబ్జెక్ట్ డిస్టెన్స్ మెజర్ చేస్తాం. అందుకని ఇక్కడ రెండు కూడా ఆపోజిట్ డైరెక్షన్లో ఉంటాయి. సో ఫోకల్ లెంగ్త్ అనేది మైనస్ అవుతుంది ఇక్కడ, నెగిటివ్. అలాగే ఇప్పుడు ఆబ్జెక్ట్ డిస్టెన్స్ తీసుకుంటే ఆబ్జెక్ట్ డిస్టెన్స్ ఇన్సిడెంట్ లైట్ రే డైరెక్షను, మనం మెజర్ చేసిన డైరెక్షను, ఈ రెండు మళ్ళీ ఆపోజిట్గానే ఉన్నాయి, అందుకే యూ కూడా మైనస్ అవుతుంది. అలాగే ఇప్పుడు v దగ్గరికి వస్తే ఇమేజ్ డిస్టెన్స్ కూడా అంతే. ఆప్టిక్ సెంటర్ టు ఇమేజ్ వైపు ఏమో ఇటువైపు వస్తాము, ఇన్సిడెంట్ రే అయితే కనుక ఆప్టిక్ సెంటర్ ఆబ్జెక్ట్ నుంచి లెన్స్ వైపు వెళ్తూ ఉంటుంది. ఈ రెండు కూడా ఆపోజిట్ డైరెక్షన్లో ఉంటాయి, అందుకే v ఈజ్ ఆల్సో negative here. Okay, so this is for concave lens. This is for concave lens. Okay, so these are the rules. Whenever if you want to use the formula of 1 by f is equal to 1 by v minus 1 by u. ఓకే, ఒక న్యూమరికల్ ప్రాబ్లమ్ని చేసేటప్పుడు కూడా ఆల్వేస్ మనం ఎప్పుడైతే మనకి డిస్టెన్సెస్ వస్తాయో ఎనీవేర్, ఎప్పుడైతే మనకి ఫోకల్ లెంగ్త్ కానీ ఆబ్జెక్ట్ డిస్టెన్స్ కానీ ఇమేజ్ డిస్టెన్స్ కానీ వస్తాయో ఎవ్రీ టైమ్ వీ హ్యావ్ టు యూజ్ దిస్ సైన్ కన్వెన్షన్స్, బట్ ఓన్లీ ఫర్ ద నోన్ వాల్యూస్ ఓన్లీ వీ హ్యావ్ టు యూజ్ దిస్ సైన్ కన్వెన్షన్. If you are finding that value means you need not to find. For example, let us suppose we know the focal length. మనకి focal length of a convex lens తెలుసు. Focal length of convex lens, let it be that is 10 centimeters అనుకుంటే ఒక ఆబ్జెక్ట్ తీసుకొచ్చి 20 సెంటీమీటర్ల దూరంలో పెట్టాం మనం, అంటే ఆబ్జెక్ట్ డిస్టెన్స్ బికమ్స్ 20 సెంటీమీటర్స్ అన్నమాట. Now what I need is image distance. Image distance ని కనుక్కోవాలి. ఓకే, సో ఇచ్చిన ప్రాబ్లంలో మనకి ఫోకల్ లెంగ్త్ ఉంది, అలాగే ఆబ్జెక్ట్ డిస్టెన్స్ యూ కూడా ఉంది. దెన్ ఇఫ్ యూ అప్లై ద ఫార్ములా 1/f is equal to 1/v minus 1/u. ఓకే, దెన్ ఫోకల్ లెంగ్త్ ఆల్రెడీ ఇచ్చారు కనుక 1/f, f is 10 and we don't know, and object distance again it becomes 20, that is like this. Okay, now we have to apply the sign conventions. As we are using a convex lens here, focal length we have to take that as positive, that is this is positive. Okay, and for the case of u, image that object distance, that also minus here. Okay, whereas when come to the image distance, here image distance we are finding, we don't know anything about that image distance, that's why here no need of applying the sign convention for v, that is. So here I am writing 1/t 10 is equal to 1/v, minus of minus becomes plus 1/20, that is. Okay, so bring that 1/20 to the other side, then 1/10 minus 1/20 is equal to 1/v. Then finally we got 1/v is equal to, if you take LCM 20, then minus 2 here and sorry plus 2 and minus 1 here, which is of 1/20 we are getting. If 1/v is 1/20, then v is equal to 20 centimeters. So means final ga manaki image distance anedi v is equal to, we got 20 centimeters, that is. Okay, so ఎప్పుడైనా కానీ ఏదైతే అన్నోన్ వాల్యూ ఉందో దానికి మనం సైన్ కన్వెన్షన్ అప్లై చేయక్కర్లేదు. యాక్చువల్గా కాన్వెక్స్ లెన్స్కి ఇమేజ్ డిస్టెన్స్ పాజిటివ్ వస్తుంది, అందుకే హియర్ మనం ఆఫ్టర్ గెటింగ్ ద ఆన్సర్ ఇఫ్ యు సీ v ఈజ్ ఈక్వల్ టు, వి గాట్ ప్లస్ 20 centimeters, that is. Okay, like this we have to do the problem of any of the, whether it is a convex lens or concave lens, we can use the formula of our lens formula. ఇదే ప్రాబ్లం ని మనం కాన్కేవ్ లెన్స్ గనుక యూజ్ చేస్తే, now I am taking same focal length, same as previous problem, but this time I am taking focal length of concave lens. If you are taking again same గనుక తీసుకుంటే, which is of 10 centimeters if you are taking, and again మళ్ళీ ఆబ్జెక్ట్ కూడా సేమ్ పొజిషన్, ఆబ్జెక్ట్ డిస్టెన్స్ ఈజ్ ఈక్వల్ టు 20 centimeters తీసుకుంటే, దెన్ ఇమేజ్ డిస్టెన్స్ వీఆర్ ఫైండింగ్. ఓకే, సో ఫర్ బోత్ కాన్వెక్స్ లెన్స్ కాన్కేవ్ లెన్స్కి సేమ్ ఫార్ములా వీ హ్యావ్, 1/f is 1/v minus 1/u, that is. Then if it is 1/f is 10 and v that is of we don't know, and object distance 20 centimeters. Then if you apply the sign convention, but as it is a concave lens, here focal length is negative and object distance also negative. Then as focal length is negative, then 10 becomes minus 10 is equal to 1/v minus 1/20, object distance also minus here. Okay, then here minus 1/10 is equal to 1/v, and minus of minus it becomes plus, so 1/20, that is. Okay, then 1/v is equal to, from this bring this 20 to the other side, 1/20 to other side, then minus 1/10 and minus 1/20, that is. Then 10 and 20 is the LCM, and again minus 2 minus 1, this is 1/v. Then 1/v is equal to, which is of minus 3/20 or minus 20/3, that is. Okay, minus 20/3, which is of 6.66 centimeters, that is. And again if you observe here, actually image distance for the case of concave lens is negative, that's why here our final answer we got, which is of v here, we got that as minus 6.66 centimeters, that is. మనకి 20 centimeters వచ్చింది, exact 20 centimeters వచ్చింది, but that too that is of positive. Positive means behind the lens మనకు వచ్చింది, ఇదేమో minus, which is before the lens we are, అంటే this is forming a virtual image and this is forming a real image అన్నమాట. Okay, so in this way we can solve any of the lens formula based problems in case of numericals. More and more examples later we will see. But the problem with this focal length formula is sometimes when you are using the lens in any other different mediums, for example, here we are taking this lens is taken in water, okay, very important example and experimentation also, that is important one as an activity purpose also. Here in the starting of this we already know that when you are taking any of the lens here like a convex or concave, I said the light ray is coming from air into the glass. Now if you are taking this convex lens which is glass, now we are taking that into any some denser medium we are taking. Means say for example, if here it is having glass is having, let us suppose it is refractive index is let us say 1.5, it's a refractive index. Now ఈ గ్లాస్ రిఫ్రాక్టివ్ ఇండెక్స్ 1.5 ని నేను ఒక మీడియంలో పెట్టాను. మీన్స్ ఐఎమ్ టేకింగ్ ఇంటూ ఆయిల్. Let it be its refractive index of this oil is 1.8. Glass యొక్క refractive index ఏమో only 1.5, here it is having more we have. So means previous case ఇది మనకి rarer medium, ఇది denser medium and light ray is coming back to the rarer medium. కానీ ఇప్పుడు ఏమైందంటే here outside surface is not air which is of, it is a denser medium for glass here. Means this is acting like denser medium, this is acting like rarer medium and again this is acting like denser medium here. Then the complete refraction pattern changes here. How that is changed? Now we will see that. For example, when the light ray is entering, here the first part we are taking, okay, like this curve. Now here we are medium taking that oil medium, that is, which is acting like a denser medium, that is. Now our glass is becoming the rarer medium now. This is of rarer, that is, okay. Now if you are taking in that denser medium, means the light ray which is coming straight like this. Now for this case the normal we have to take is, let us say for example, this is the normal for this surface. Then what happens there is the light ray actually as it is coming from denser to rarer, the light ray has to move away from the normal like this, okay. But if you remember, convex lens actually it is having a converging nature, but here if you observe it is showing diverging nature, which is very clear that, and very important point also here, when convex lens is placed in a denser medium, the converging nature becomes diverging, okay. సో ఎప్పుడైతే మనం ఈ కాన్వెక్స్ లెన్స్ని కనుక మోర్ దాన్ ఇట్స్ రిఫ్రాక్టివ్ ఇండెక్స్ ఉండే మీడియంలోకి అయితే తీసుకెళ్తామో దాని కన్వర్జింగ్ నేచర్ కాస్త మనకి డైవర్జింగ్ అయిపోతుంది, ఓకే. ద కంప్లీట్ నేచర్ ఈజ్ డిఫరెంట్. అండ్ ఇన్ ద సేమ్ వే ఇప్పుడు కనుక మనం సేమ్ ఇఫ్ యు ఆర్ అప్లయింగ్ ఫర్ ద కేస్ ఆఫ్ కాన్కేవ్ లెన్స్, ఓకే, ఇన్ కేస్ ఆఫ్ కాన్కేవ్ లెన్స్ we are taking like this, okay. In case of concave lens again we are taking the outside which is a denser medium, this is going to be act like rarer medium which is our glass having refractive index 1.5 and denser medium which is like oil having refractive index 1.8, let it be, okay. అప్పుడు మనకి ఏమవుతుందంటే here if this is the curved surface we are taking, here we are having the denser medium there, oil, and here I am taking a light ray in that, okay. So this is the denser medium and it is entering into the rarer medium, and for this surface now we are taking the normal like this it comes, okay. అయితే ఇక్కడ as the light ray is going from denser to rarer, it has to bend away from the normal. So that's why it is bending like this, away from the normal. But actually this is a concave lens. Concave lens, its nature is actually it has to diverge. But in this case, now it is starting converging the light rays, which means here again the same thing. When convex lens, this time, when concave lens now, when concave lens is placed in a denser medium, its diverging nature becomes converging, but this time a bit different one, of which here we are taking a special case of convex lens numerical problem, which is the object is placed in between focus and optic center, of which let us suppose if the focus of the convex lens focal length, the focal length of convex lens if you are taking, which is let it be that is of 15 centimeters, that is okay, that is of 15 centimeters, but object is placed u, it is of 10 centimeters if it is placed okay at 10 centimeters, that is. Then if we clearly we know that focus is at 15, but object is placed at 10 centimeters, which means like this sixth ray diagram we got. Focal length is at 15, object is at 10, like this. This is the special case, okay, of which if you remember the image is formed on the same side, like this you will get. Okay. Then if object is at 10 centimeters here, then in this case, if you find the image distance, again 1 by f is equal to 1 by v minus 1 by u here. As focal length it is of 15 centimeters given already, and we are finding for image distance. So that object distance is 10, that is. And if you apply the sign convention, as this is a convex lens, focal length is positive, object distance is negative for that. Then 1 by 15 is equal to 1 by v, minus of minus becomes plus 1 by 10. So 1 by v is equal to 1 by 15 minus 1 by 10, that is. So if you take LCM 15 and 10, which is of 30, and here 2 minus 3, which is minus 1 by 30, that is. If 1 by v is minus 1 by 30, then v becomes minus 30 centimeters. Actual sign convention for the case of convex lens is a positive one, but here v value we are getting negative, which means the image which is formed is opposite to the incident light ray direction. Only in this special case we have to remember that, because this is the incident light ray direction, but here if you measure the image distance, we have to measure starting from origin. No? So that's why here we are taking the image distance like this. That's why the incident ray and the image distance which we are measuring, both are in the opposite direction, we are measuring that. That's why here we are getting the image distance as negative value, that is. Okay. In the same way, here in case of if you want to find the object distance, okay, let us suppose the same problem here I am doing like this. If the focal length of convex lens is 15 centimeters, and now what I am doing is I got a virtual image at 30 centimeters. Whenever I said if I got a virtual image at 30 centimeters, which means virtual image is formed on the same side of the lens here. So that's why if you apply the sign convention 1 by f is equal to 1 by v minus 1 by u, then 1 by f is equal to, where f is given as 15, v 30 and u we do not know. As it is particularly mentioned as it is a virtual image is there, we know that focal length is positive for convex lens, whereas when come to image distance we cannot take that as a positive. We clearly mentioned there in the case of sign convention also there, that sign conventions we took for the case of convex positive, that is for real image, but this is for virtual image, whereas virtual image is formed on the same side of the lens. So that's why here you have to take V value as minus 1 by 30, then 1 by 15 is equal to minus 1 by 30 and minus 1 by u. That minus coming this side becomes plus, which is 1 by 15 plus 1 by 30 is equal to minus 1 by u, that is. Okay. Then 1 by 15 plus 1 by 30, LCM becomes 30 there, and again here we will get 15 means 2 plus 1 is equal to minus 1 by u, that is. Then minus 1 by u is equal to 3 by 30, which is of 10 get cancelled. Then minus 1 by u is equal to 1 by 10, u is equal to, we will get minus 10 centimeters, like this. So that's why whenever if you are solving a problem by using this lens formula, at first we have to check the position of the image. Is that a virtual or is that a real? 1 by f is equal to 1 by v minus 1 by u. Actually that is only for thin lens, means we never consider about the refractive index of the glass we are using inside there. But some cases we have to use when you are using that double convex, double concave lens. Actually the thickness also matters here. Like we saw that in the previous sessions there, that thickness actually affects the refractive index here. So that's why when you are using a double convex or double concave lens, okay, we have to use another formula, that only call that as lens maker's formula. That is lens maker's formula, that is, and this is called lens formula, and this is lens maker's formula, that is. And according to this formula, as 1 by f is equal to, here the refractive index whatever you are taking for that material of the lens, mu refractive index, mu minus 1 into 1 by r1 minus 1 by r2, this is the formula. And what are this r1 and r2 means? Whatever the convex lens or concave lens you are taking, a double convex or double concave, both are part of a glass spheres, that is. For example, this lens is taken from one and this curved surface is taken from another lens here. Now the distance of the center of curvature from optic center, this distance we call that as r1, and this distance we are taking that as r2, like this, because both are taken from two different spherical glasses. So that's why we are getting the combination of both of that, of which we are getting that r1 and r2 there. Radius of curvatures are different, and this is used for when you are using a thick lens, means having a refractive index matters here. Okay. Now for suppose if you are using this one, which is a double convex having refractive index mu is present, for those type of cases also we have to apply the same sign convention here, but in a different way we will apply the sign convention. For example, here I am taking the refractive index of the glass is 1.5, so that I am using a very thick glass there. This glass is having refractive index 1.5, that is. Okay. Now when we are applying the formula of 1 by f is equal to mu minus 1 of 1 by r1 minus 1 by r2. Now actually the light ray is coming from air into this lens, coming from air into this glass. Now whenever the light ray is entering, here the surface is like a convex surface outside that, okay, that is acting like a convex surface. This is about r1. The light ray where it is incidenting, that side we are taking that as r1, and the other side we are taking that as r2, that is. Okay. So here on the r1 surface here actually we are taking that incident light ray there. Okay. And let us suppose the first case r1 is equal to, let it be that is of 20 centimeters. Okay. And let us suppose r2 is equal to 30 centimeters, that is. Okay. Now if you are taking 1 by f is equal to mu minus 1 of 1 by R1, where R1 is 20 and R2 is 30. Just like our previous problems, even now also directly we are substituting the values. We know the value of mu, which is 1.5 minus 1, and 1 by R1, which is 1 by 20 minus 1 by R2, which is 30. But while applying the sign convention only, we have to be very careful here, because this is the radius of curvature. We know that R is equal to 2f. Okay, then whatever the sign convention we are having for the focal length there, the same sign convention it comes even for the case of radius of curvature also. Okay, so that's why here whenever the light ray is entering onto the R1 surface, here it is having a nature convex. Convex lens focal length is positive. That's why here R1 is also taken as positive here. Have understood now why R1 is a positive? Because whenever if you are taking a double convex lens like this, a double convex lens, on which side the light ray is incidenting, here this part we are taking that as R1. As it is taken as R1, okay, and it appears to be like a convex surface there, that curved surface, that is like a convex surface. For convex lens, the focal length is positive. So that's why for R1 also the focal length we are taking, that R1 we are taking the sign convention as positive, that is. Now the light ray enters into the glass, okay, like this. Now whenever it enters into the glass to the other surface, which is R2 surface, if we are taking inside the glass, okay, now the surface is appears to be like a concave surface, that is, see, that is like this. Okay, here it is incidenting inside the glass. Okay, this surface is our R2, and actually it appears to be like a concave surface, that is. If it is a concave surface, then focal length is negative for concave surface. So that's why here for the case of R2 it becomes minus like this. Okay, then if you substitute that 1 by f is equal to mu minus 1 of 1 by 20 minus of minus plus 1 by 30, that is. Okay, then if you calculate that 1 by f is equal to mu value already given, mu 1.5 minus 1 of 1 by 20 plus 1 by 30, where LCM is 60, 23s and 32s, that is. Okay, then 1 by f is equal to 1.5 minus 1, which is 0.5 into here 3 plus 2, 5 by 60, that is 5 ones and 5 12s, that is 60. Okay, then 1 by f is equal to 12 by 0.5. 0.5 means 5 by 10, of which f is equal to so 12 into 2, 24 centimeters, that is. Okay, this is the focal length. But if you observe here, the final focal length we are having the sign convention plus, because we are taking a double convex lens. So that's why here the final focal length we are getting is a positive focal length we are getting, f is equal to 24. Okay, so note that here while applying for the case of R1 and R2, R1 first surface where the light ray incidence, R2 is nothing but whenever the light ray comes inside that lens here, which surface is present, that is taken as R2, that is. Okay, this is for the case of a double convex lens, and we are applying here the lens maker formula. Okay, now the same case, for suppose if you are using a double concave lens now instead of convex lens, for the same formula I am taking, but the lens I am using is a concave lens we are using. Okay, like this, a double concave lens. Now as R1 is equal to 20, R1 we have to take always where the light ray incident on a surface, that surface only we are taking that as R1 surface. So this is going to be R1 surface if I am taking the light ray like this. Okay, as it is coming onto the R1 surface, that R1 surface is appears to be like a concave surface, that is. If it is a concave surface, if you apply the formula 1 by f is equal to mu minus 1 of 1 by R1, which is a 20, 1 by R2, which is 30, that is, then 1 by f is equal to mu, which is 1.5 minus 1 of 1 by 20 And the sign convention here, as it is a concave surface, its focal length is negative we have, then 20 becomes negative, minus 1 by here 30 is there. This 30 it is about second surface here. Our second surface is this one, which is R2. When the light ray is striking this R2 here, when the light ray is striking that R2 here, it appears to be like a convex surface. See, like this. This is for R2 and this is for R1. R1 is like concave, R2 is like a convex surface here. If it is a convex surface, we have to take that as positive, that is. So, that is why here 30 is plus only we have to take. Okay. Then 1 by f is equal to 1.5 minus 1, which is 0.5 of minus 1 by 20 minus of plus again minus 1 by 30, that is. Then 1 by f is equal to 0.5. We can also write that as 1 by 2 into, if you take LCM 20 and 30 again, 60 minus 3 and minus 2, that is. Then 1 by f is equal to minus 1 by 2 into minus of 5 by 60, that is. Then we are getting f is equal to minus 24 centimeters. Again, if you see, as this is a concave surface, again we are getting minus the focal length here. So, this is for the case of a concave lens. Mainly two important things here while applying the sign convention. Okay. So, the surface which the light ray is incidenting, always you have to take that as R1, the other one is going to be R2. And how to use this sign convention, whether it is a convex or concave, is when the light ray incident on a surface, observe the surface. If it appears like a concave surface, like in this case, take that as minus. If it appears to be like a convex surface here, then take that as plus. Okay. So, that is why here we got minus 1 by 20 and minus of plus becomes minus 1 by 30. Okay. This is for the case of lens maker formula. These problems of lens maker formula, it need not to be every time we have to take R1 and R2 values may be different. Sometimes we can take R1 and R2 values, both may be equal also possible. Equiconvex lens, okay, or equiconcave lens, that is. Okay. R1 is equal to R2 equal to R. Like this also you can take. Okay. For suppose if you are taking R1 is equal to R2 is equal to R, then how the focal length is going to be is like this. 1 by f is equal to mu minus 1 of, okay. Let us suppose again refractive index mu is 1.5. Okay. Then mu minus 1 of 1 by R1, which is 1 by R, minus 1 by R2, even that is also R, that is. But if you are applying for the case of a double convex lens, like this, as I said before, the surface where the light ray incidents, that is R1, the other side is going to be R2, that is. Okay. If you are taking that is R1, again R1 surface is like a convex surface. This is a convex surface. Okay. Then as it is a convex surface, then R sign convention is, as focal length is positive, that R1 sign convention also becomes positive here. Whereas the second one, which is the light ray after refraction entering into the glass here inside the lens there, now it is incidenting on the other surface where that is R2 here. But whenever it incident on the second surface R2, again if you observe, that is like a concave surface, that is a concave one. As it is a concave one, here we have to take that as minus for the focal length. Then 1 by f is equal to mu minus 1 of 1 by r, minus of minus becomes plus 1 by r. Then 1 by f is, as mu is 1.5, minus 1 of 1 by r it becomes 2 by r, that is. Okay. Then 1 by f is equal to 1.5 minus 1, which is 0.5 into here 2 by r is there. Okay. Then 1 by f is equal to 0.5 into 2, which is 1 by r, then F becomes finally it is equal to R. So means if you are taking a equi-convex or a concave lens where R1 is equal to R2 equal to R, in those cases the final focal length of the double convex lens you are taking, that also is equal to the radius of curvature given there, one of the radius of curvature, because here both are same, R1 is equal to R2 equal to R, that is. This is for the case of a convex lens. But you can apply the same thing even for the case of concave lens also, but just by changing the sign convention here. Okay. Now how that is, now we will see. For example, the same case of which R1 is equal to R2 case, now we are taking for the case of a concave surface, concave lens. So means like this, here we are taking a concave lens, a double concave lens. Okay. Now again, as I said, incident light ray surface always is taken as R1, other side is taken as R2, and here if you observe the first surface is like concave here. The other side where the light ray is striking, this is going to be convex, that is. Okay. Now mu minus 1 of mu minus 1, which is 1.5 minus 1 of 1 by R1, which is taken as R, where it is a concave surface is present, that is why it is taken as minus here. Okay. Minus of 1 by R2. R2 is also R only, but here the surface is different, which is a convex surface. Convex surface actually we are having positive is there, so means plus. Then 1.5 minus 1, which is 0.5 into here minus 1 by R, and minus of plus minus 1 by R, that is. Then 0.5, which is 1 by 2 into minus 1 by R, minus 1 by R, minus 2 by R, that is. Then again we are getting minus 1 by R. This is for 1 by F. Then F is equal to, finally we got minus R, like this. Okay. This is for the case of concave lens. Okay. Previous one is for convex lens, now this is for concave lens. From this we can conclude that you need not to take every time that R1, R2 values may be different. Sometimes we can take a equi-convex or a equi-concave, so that R1 is equal to R2 is also equal to R also we can take here. Of all these refraction through these curved surfaces, how we are getting the questions in the competitive exams? Actually mainly here we discussed about, first one we discussed, which is of behavior of refraction through lens here, which is about rules for drawing ray diagrams there. Rules for drawing ray diagrams. Based on this, how the questions they will ask is, for example like this. A light ray passes through principal focus of a convex lens, then after refraction, okay, option A, it is given as, let us suppose, as it is passing through principal focus, passes parallel to principal axis, that is one, and option B given, passes undeviated, and option C given, the angle of incidence and angle of refraction is equal to 0, and option D, light ray passes through focus on other side, like this. These are the four options given. See here, if a light ray passes through principal focus of a convex lens, then after refraction, actually here it is passing through principal focus. If the light ray passes through principal focus or any of the light ray which is starting from principal focus, after refraction, what happens there is the light ray has to go parallel to the principal axis. According to which one rule? 2, that is, if this is the convex lens and given that the light ray is passing through the principal focus, means like this. Then after refraction, actually the light ray is going parallel to the principal axis, that is. So means of the given options, our A is correct, like this. Okay, have understood now? In the same way, for suppose if it is given like this, same question, for the same, based on the same rule 2 only, they may ask like this also. To get a light ray parallel to principal axis by using a convex lens, then the light ray should pass through, like this. Same question only in a different way. Here, to get a light ray parallel to the principal axis, means I want to get a light ray here which is parallel to the principal axis there. Then by using convex lens, that is, then the light ray should pass through. So if I want to get that parallel light ray here, the light ray should pass through principal focus here, like this. These type of questions they may ask either about the refracted ray or about the incident ray, where the light ray is started, how the light ray is moving, like that, about the incident ray or about the refracted ray. That is based on rules for ray diagrams they will ask. And if you are taking next one about the ray diagrams, if you take, okay, in case of ray diagrams, okay, in case of ray diagrams if you are taking, in case of ray diagrams, most of the cases they will ask about how the image is formed and where the image is formed, or what is the position of the object, then what about the size, okay, like these type of questions they will ask. So that's why here for the case of ray diagrams always we have to prefer taking a table of that. Okay, for example, if you are taking for the case of convex lens, okay, that convex lens ray diagram table we can draw like this. For example, first we are taking the object position, which are of total 6 positions we have, of which object at infinite and C, at C, and between C and F, and between F and O, the optic center there. Okay, and the next one we are taking image position is there. For the case of image position, here if object is at infinite, the image is formed at F, between infinite and C, image is formed in between F and C at the center of curvature, and after that between F and C and infinite, and after that infinite, and finally we got before the mirror, before the lens, that is special case. Okay, and after that we are having nature. Other than the last case, all cases we are having the same type of nature, which is real and inverted. Here also real and inverted. Here also real and inverted. And here also real and inverted, real and inverted. Now we are taking the last case, which is the special one, that is of virtual and erect case, that is. Okay, and finally the size. Okay, if you are taking the size of the object, the size, gradually when the object is coming closer, the size of the image gradually increases here. That is of here it forms diminish, which is of highly diminish, next is diminish, and after that same size, and after that enlarged, and after that a highly enlarged, and last one is also highly magnified one we are getting. Okay, like this. This is our ray diagram table. Now how the question they will ask in the exam is, for suppose if I want to get a convex lens, by using a convex lens I want to get a real and same size image, then where to place the object. So object is placed at center of curvature. Or if you are getting a same size image there, then what is the position of the image? Image is at the center of curvature. Or if you are taking the object is in between infinite and C, what is the size of the image? Size of the image is diminish. That is our answer. Like this. Or they may ask like this also. If you are getting a real and inverted image in between C and infinite, where is the position of the object? So object is at in between C and F. Or what is the size of the object image there if the object is in between C and infinite? If object is between infinite and C, the size of the image is diminished. If the image is formed between C and infinite, the image is formed, the image size of the image formed there is enlarged image here, like this. Okay? Or they may ask like this also. If you want to get an image exactly on the focus here, then where to place the object? So object is placed where? At infinite. Like this, most of the questions we are getting from ray diagram like this, depending on the object position, depending on the image position, depending on the size we are taking. Okay? So 6 different cases, 6 ray diagrams we have. And lens maker formula is 1 by f is equal to mu minus 1 of 1 by r1 minus 1 by r2. Based on this, how we are getting the question is about the focus or the focal length here in case of this convex or concave. As I said before, this depending on the medium you are taking, here the convex lens sometimes behaving like a concave lens and sometimes concave lens is behaving like a convex lens. But while applying this any of the formula f, v and u, or even for r1 and r2, always we have to apply the sign convention here. Okay? And in case of finding this 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2, this formula we have to use if there is a thick lens is present. And this one we use when there is a thin lens is present. Means we are not considering about the refractive index in case of first one, which is 1 by f equal to 1 by v minus 1 by u. Okay? Whereas in case of this one, here 1 by f equal to mu minus 1 into 1 by r1 minus 1 by r2, where r1 is the radius of curvature of the first one, r2 is the radius of curvature of the second one. Here you can take any of the lens which is of here need not to be r1 and r2 different. Sometimes we can take r1 is equal to r2 here. But whenever you are taking that r1 is equal to r2, then you have to apply the sign convention case there. Okay, and we already done the example there. Based on that, if you take mu is equal to 0.5, we got that f is equal to r here when mu is equal to 0.5. Okay, so like this we have to apply the sign conventions if you are using a lens formula or a lens maker formula. And while doing about the ray diagrams here, you have to remember about the position of object, position of the image and the size here.